Hey, let's talk about key encapsulation mechanisms. In the lecture, you have seen this hybrid encryption construction, which is a public key encryption scheme that works as follows. Essentially, you generate a random symmetric key, so a random key for a private key encryption scheme. Then you encrypt that key with your public key encryption scheme, and then you encrypt the actual message using the private key encryption scheme. And then the overall ciphertext contains both the encryption of the data and the encryption of the key that the data is encrypted under. And this thing is really standard. So I've never seen anyone use a public key encryption scheme like RSA or Elgamal to encrypt anything other than an actual key for a symmetric encryption scheme that is then used to encrypt the data. And because it's used so much, these things actually have names. And the name for this encryption here is the data encryption mechanism. And this is the key encapsulation mechanism, because this thing here encrypts the data and this thing here encrypts the key. And today I want to talk about this KEM part a bit more. So how do we encrypt keys with a public key encryption scheme? It turns out we can be a bit more efficient about this than this construction suggests. The key observation for this is, in this construction, the public key encryption scheme is only ever used to encrypt random values, namely these random keys here. And let's just say that's actually without loss of generality, these keys are just random bit strings. Then the only role of this encryption scheme is I am giving you a random bit string, and then you give me a ciphertext for that. This encryption scheme will never see an adversarially chosen message. So in this case, we don't need the full power of public key encryption schemes. We just need them to encrypt random messages. So the thing that we're going to do now is we will take a look at this process here and come up with a scheme that actually does exactly this process. So a scheme that will generate a random key and a ciphertext for this random key. And this sort of a scheme is what we call in cryptography a KEM, a key encapsulation mechanism. It's basically a public key encryption scheme, but you can't give it messages to encrypt. It will always just give you random messages and the ciphertext for that. So looking at this, there's a key generation algorithm that outputs a secret key and a public key. There's an Encaps algorithm that's kind of like the encryption algorithm, but this thing doesn't take any input. It will instead output a random key and a ciphertext for the key. Finally, there's the decaps algorithm, and that thing takes the ciphertext from here and outputs the key k corresponding to it. Then correctness for these schemes, how are they supposed to work, says that someone generates a public key secret key pair. Then I can take this public key and I call encaps, and then encaps may give me a k and a c. The k I will keep secret, and the c I can just send over an insecure channel. And then if the receiver of the c calls decaps, he will get the same key k from that. So one example used for this would be here in this hybrid encryption scheme, where I would replace this part here by which will generate me k and an encryption of k. And then you would use the key k that you got from the encapsulation as the private key in our private key encryption scheme to actually encrypt the message. And in this use case, also this decryption here just becomes decaps. Now we need some sort of security notion for these key encapsulation mechanisms over here. The problem is that the usual way, like how we usually define security for encryption, is that we let an adversary give us two different messages. Then we pick one of those at random and give him the ciphertext for that message. But that's something we can't do here because the Encaps algorithm doesn't take a message. So there's nothing to choose for the adversary. That's why we define security for a KEM in a real or random decision game. So there we have an adversary A, and that adversary A lives in one of two possible worlds, similar to what you've seen in the PRG definition, for example. In the first world, we give the adversary the ciphertext C, and we give it the actual key that's hidden in C. In the other world, we also give him the ciphertext C, but we, instead of K, give him R, which is a random bit string that has nothing to do with the actual value that's hidden within C. And obviously the adversary also gets the public key because that's publicly available, so we should give it to him. And then this definition says that the adversary cannot tell in which of these two worlds it is. So it can't tell whether it gets an actual K or it gets a independently random R. So this means that if I give an adversary a ciphertext C, then from this ciphertext it doesn't learn anything about the key. In the strong sense even that even if I give it the key, it won't be able to tell whether this is actually the correct key or it's a key that has nothing to do with it. And then this works if we use it in this hybrid encryption scheme similarly as we did before. Just that in the proof of the hybrid encryption scheme, we replaced the public key encryption of the secret key K by just an encryption of 0. We can't necessarily do this with a KEM because there is no encryption of 0 in this sense. So what we would do in the proof instead is we don't replace it by 0, we just replace it by a random key that has nothing to do with the actual secret key K. But this is functionally the same. So then as soon as I have replaced this encryption of the key K with an encryption of some unrelated thing, I get into this world where this public key encryption part can just be simulated without any knowledge of the secret key K. So basically the same security proof applies, we just don't replace the public key encryption with encryptions of 0, but just with an encapsulation of something that doesn't have to do anything with the secret key K. Obviously we can construct a KEM from a CPA secure public key encryption scheme. Because essentially a KEM is a public key encryption scheme, just that it has lost its ability to encrypt arbitrary messages, it just encrypts random messages. So we can do the same thing that we did in the hybrid encryption scheme too. We just choose a random key, and then we encrypt that key with the public key encryption scheme. So that's what Encaps would do. And then it would just output the key K and the ciphertext C. And then everything works because decaps would just recreate K. But why do I say this is inefficient? Think about how every single one of the public key encryption schemes that you've seen, what those look like. They've all been of this form. They contained a part where they have blinded the message with some random looking value. And then they provide a decryption hint in the ciphertext, which basically allows you to recompute this something random looking here using the secret key. Now the big idea of KEMs is just the second part here. We are just XORing a randomly chosen K with something that's already random looking. So that's pretty much redundant. And so we can just get rid of this part. So basically what all of this KEM stuff will boil down to is if we have an encryption scheme that has this form, that it provides a decryption hint that allows you to recreate something that's looking pretty random, that was there used to blind the message. Then we just remove this part with a blinded message, and our KEM will just contain this decryption hint. So the ciphertext is definitely much smaller now because it doesn't contain this second part anymore. It just contains the decryption hint. And then there's something random looking, will just be the key K, which means it's something that you can just recreate using the secret key. That's what was used for decryption previously. And it's something that you also compute during the encryption part because you need to compute it in order to XOR it with your message. So it's something that the Encaps algorithm would also be able to output. So let's try to actually instantiate this idea. From the lecture, you should recall this construction of public key encryption from trapdoor permutations with a hardcore bit. So the person who encrypted a message chose a random X and compute the hardcore bit of X and then use that to blind the message. So this hardcore predicate here is the thing that looks random. And then the ciphertext also contained a decryption hint so that the person who actually has the secret key, which is the trapdoor to the trapdoor permutation, will be able to decrypt by recomputing X from f of X and then computing the hardcore predicate. So then if we apply our idea, we can make this a key encapsulation mechanism, an efficient one, or a at least slightly more efficient one, for single bit keys, which is, well, it's at least a start. So the key generation is as before. The secret key is the trapdoor for the trapdoor permutation, and the public key is the index or like the parameters for the trapdoor permutation. To encapsulate, you sample a random pre-image X. The ciphertext is just f of X, which corresponds to the decryption hint part that we had before. And the actual random key is the hardcore bit of X. And then you can obviously decapsulate this by inverting C and then evaluating the hardcore bit on X. Now for security, remember that the definition said that if I give an adversary C and either K or some random value, then he can't distinguish which of these two I give him. And for this instantiation, this is easy to see, because C is just f of x, and K is the hardcore bit. So in that case, the definition says if I give you f of x, you can't distinguish the actual hardcore bit from just a random bit. And this is actually pretty easy to see, because if you had an adversary that would be able to distinguish the actual hardcore bit of the x hidden in f of x from just a random bit, then you could use this adversary pretty straightforwardly to actually compute the hardcore bit. The idea would be you just give it your f of x for which you want to compute the hardcore bit, then you give it also a candidate hardcore bit, and it will tell you whether or not you were right, very roughly. So just a quick question for you. What happens if we use this KEM in a hybrid encryption scheme? And let's say as the symmetric encryption scheme, we just use the one-time pad. Yes, exactly. We get back our original encryption scheme, because this first part here will have become our C1, and the second part here is just our C2, which is a one-time pad encryption of M under the key K that's chosen from the KEM. And that's actually kind of interesting. All of the encryption schemes that we've seen, they all follow this, this pattern of they have a decryption hint, and then they have a part where they XOR a random looking value with a message. So at their core, these things are basically all just KEMs. That's the decryption hint, that's like the important part. And then we just throw hybrid encryption with the one-time pad onto that. Let's look at some more examples. So this KEM that we've just seen is a little bit boring, because the secret key that it outputs are just single bits. So it's pretty much only useful to encrypt single bits with. But last week we've seen other encryption schemes, and one of those was the RSA-based encryption scheme with the random oracle. So there, if you wanted to encrypt something, we chose a random x from Zn. And then the ciphertext was x to the e, which is basically the RSA trapdoor permutation applied to x. And then we blinded the message with the hash value of x, where we modeled h as a random oracle. And then the security proof was basically, in order to gain any information about the hidden message m, you would have to query the random oracle for x, and that should be hard, because just given x to the e, you should not be able to recompute x without the trapdoor. But with the trapdoor, you could take this x to the e, raise it to the power of d, you get x back, then you can hash that, and you have your message back. So what does the corresponding KEM for that look like? So this is pretty straightforward. The key is the thing that we also use here in this one-time pad fashion, that's just h of x, and the actual KEM ciphertext is just x to the e. And proving that this is a secured KEM is almost trivial, because you need to decide whether you get k or a random value r. And obviously an adversary can only do that if it actually computes x, given x to the e, and then creates the random oracle with that, and then can basically check whether this is the same. Our computing x is hard, and we could use this capability to construct our own RSA inverter, so this is not an attack that can actually happen. And notice here that using this RSA KEM is actually much more efficient than using this RSA encryption scheme to encrypt a random key, because basically the only thing that you need to send alongside your symmetric ciphertext is just x to the e, instead of x to the e plus this whole image with the random key. Also last week we've seen the Elgamal encryption scheme. There the secret key was a random exponent, and the public key was g to the secret key. And then if I wanted to encrypt something, I took the public key, I chose a random r, raised the whole public key to the power of r, also raised g to the r, and then used g to the sk times r to blind m with, where m was a group element. So what's the corresponding KEM for this Elgamal encryption scheme? So what's the Elgamal KEM? Yep. Here actually we would have to change the KEM definition a little bit, because the key that's output by the KEM is a group element, which doesn't necessarily look like a random bit string. So there we would have to replace it with K cannot be distinguished from a random group element. But yeah, that works. Notice that in this case, we're not using the one-time pad per se to blind it, but we're using kind of a variant of the one-time pad. So we have this random group element and we multiply that with a random message, which is kind of the same as taking a random bit string and XORing the message onto this. So yeah, that's the whole thing about key encapsulation schemes. Basically, we've seen them all along. We just have never called them this. Part of the generation of a ciphertext in normal public key encryption schemes is already coming up with a random value to blind the message with. So just use that as a key for AES or whatever you want to do in your hybrid encryption scheme. And by basically looking under the hood of all of these encryption schemes that we use for this construction 1017, the hybrid encryption, we were able to improve the number of bits in our ciphertext that we need to send by cutting down on some parts that are actually kind of redundant. All right, that's that. Thanks for listening and see you.